So somebody asked over email to work the spring 21 with the resistors, and then I think one of you wanted to go back and look at some capacitor circuits, so we'll do that from the free response. And then if you have any specific questions, we can address those. So you will have a question like this where it's a combination circuit. It's going to be similar difficulty with a similar number of resistors, but probably different in the way that it's laid out. But the approach is still the same. So you just begin by simplifying the circuit, and I recommend that you draw the circuit. You should have time. In this case, I'm going to simplify these two. So I have a 12-volt battery with, I'm going to go ahead and actually simplify these two 2-ohm resistors right here. 2 and 2 in parallel, that's 1 ohm. That's 1 over a half plus a half, that's 2. And then I'm going to have a 3 ohm, and then up top 2 plus 4 is 6 ohms, and then 3 ohms, and then that goes back. I have 12 volts there. And then the 3 and the 6 in parallel, that's equivalent to 2. So I have a 1 ohm and a 2 ohm with 12 volts. And then the 1 and the 2 ohm, of course, is 3 ohms. So I have that's my final equivalent resistance. I don't think that I asked for your equivalent resistance in this. I just asked a voltage or current across one or 2 or 3 resistors. But it's useful to get it because then I can find the current. Current is V over R, so that's 4 amps. That means that, resistors in series have the same current. That means that both of these have 4 amps. Resistors in series have the same current. Resistors in parallel have the same voltage. Okay, remember those rules. Hopefully you've memorized them by now and been using them over and over. So this 4 amps is the same for this one, that 1 ohm resistor. And then the 4 amps here comes through and it splits up into 2 pieces. I need to figure out what those 2 pieces are. But look, I know that this resistor has 8 volts and this resistor has 4 volts. The reason I know that, I know the voltage, the current and the resistance. 4 times 1 is 4. 4 times 2 is 8. So that gives me 4 volts here, and it gives me 8 volts here and 8 volts here. So now I can go back and figure out the current in each of those resistors. The current here is 8 volts divided by 6 ohms. That's 4 thirds amps. And then down here, I have 8 thirds amps. If I want to just check that, I can say 4 thirds plus 8 thirds is 12 thirds. That's equal to 4. Joe? I don't care, but I find it's a little easier to do it in fractional form. Okay, that's fine. If you want to do it in decimal, that's fine. All right. So now that I know that current, I know that both of these resistors have 4 thirds amps, and I can copy over some of these other things. I know these two both have 4 volts because they're in parallel, so they have the same voltage as their equivalent. This one I'd already seen has 8 volts. So now it's a matter of just figuring out what is the voltage across R3 and R4. But since this resistor had 4 thirds amps, remember how I got that? I said this has 8 volts over 6 ohms, so that's 4 thirds amps. That's also the current through these 2 resistors. Both of those have 4 thirds amps. So 4 thirds amps on both of them. Sorry. 4 thirds amps on each of those. And then if I want to find the voltage, which I wanted to find the voltage on, it's just going to be I times R. 2 times 4 thirds, that's 8 thirds volts. And 4 times 4 thirds, that's 16 thirds volts. 8 plus 16 is 24 divided by 3, that's 8 volts, which I know is what I had on the equivalent resistor. Gosh, I don't remember if I had fractions. There might have been like 1 or 2 fractions that slipped in on that. I try to keep the fractions away. I know that y'all don't like that. Right? Y'all don't like that? Fractions? Decimals? I try to make the numbers as easy as possible, but I can't guarantee that there are no fractions. Have the same volts. Okay. So remember those rules. Those rules are really important. We wrote those stuff down several times in the notes. We did this one page where it had all the resistors and capacitors. So, really actually you can write on your mobile form just to help you remember those sets of rules. They're very similar, which is good because it makes them easy to remember, but it's also bad because it makes them easy to get mixed up too. Okay, and then somebody wanted to look at just several different capacitor circuits because you will have one like this one, for example. I think just in particular drawing them in a way that's just easier to see, because I do intentionally draw them in a way that's not the normal way that we draw them, because that's how you encounter them, in real life when you're working on capacitor circuits. When you graduate, you become whatever it is that you become. Right. It's good for spatial thinking too. Like I like that too. It helps you to develop good spatial skills, and that's important. So on these, I always start on the big side of the battery. I follow along and I come up to this point, and I enter a junction, and you might say that that junction only has 2 parts to it, but it actually has 3 parts. And I can tell that because, this is one branch, this is the second branch, and then I have a third branch right here. So effectively, if there are no capacitors or devices or anything in between all these little junctions, I can collapse them all down to a single point. So that's a good way to think about it, that if there are no devices, I can get rid of all those little junctions and just collapse them down to a single point. So let's go ahead and do that. I'm going to draw the 12-volt battery. I have 3 branches. I have the 3 microfarad, the 2 microfarad, and then over here I have the other 2 microfarad. So I have those 3, and actually in this third branch I go around the corner and then there's another 2 microfarad. And then even though it does have this funky thing where all this stuff all breaks up, notice that there are no capacitors down here, so I can collapse all this whole nest of wires just down to a single point. And what that looks like on the circuit is they all come back right here. Okay, all this stuff right here all becomes a single point, because it doesn't affect the circuit if I make those all together, because there's no capacitors there. We just draw those extra lines to sort of lay the circuit out on this grid-like pattern. And then after that I have C5, so that is the 3 microfarad capacitor. Okay? And then from there, you do a lot like what we did with the combination circuit, except applying the rules for the capacitors. Let's look at a different one. We can come back to this one if y'all want, but let's look at a different one. There was one that was kind of wonky. Yeah, I think it was this one. Right, this one's kind of wonky. This one's a little bit different. Listen, if you can do all the circuits that I have on the free response, there's 4 or 5, you should be fine. They'll be similar to one of those, okay? So, hey, what? Which exam is this? This is spring 20. Exam 2. Don't forget, there are some questions on exam 3. If you run out of things to practice, you can go look at the exams 3, those highlighted questions on exam 3. There weren't that many. But so, again, start at the big side of the battery and go in that direction. I find that that's easier. So I have the 12 volt. I go to a 2 microfarad capacitor. There's no branches before that point. Right, so I go through there, and then I come to a branch, a junction. And how many parts are there in that one? How many branches in that parallel? There are just 2, right? I have this one and this one. So I'm going to go to that parallel with 2 branches, and I have the 2 and the 4 microfarad. And then that all comes back together to this part. And then how many are in that parallel branch? How many branches in that parallel part, right? That parallel part. There are 2, right? There's this one, and then there's this one. So I have the 1 microfarad, and then I have the 4 microfarad. Okay? This is where it gets It's not really difficult, but it gets a little strange, but because this 4 microfarad then traces back over here, and I get another 4 microfarad. I go through the 1 microfarad, and then they all come back together here. And then that's that circuit, which, when I draw it like that, it doesn't look that scary. It actually looks like one that we've done a number of times. Yeah. Why did I flip it? Oh, no, I could have done it that way. Okay. No reason. It's still the same. What I did though is I started on this high potential side of the battery and just went through each part of the circuit. So if you go through carefully and just follow, where the wires go and where you cross over junctions, you should be able to redraw that circuit without much difficulty. Just a second.
For the bottom part, the one is because why is the one and four? Why are they not?
Why are they not together? I got you. Let me show you. Look, between this 4 microfarad and the other 4 microfarad, there are no junctions. So they have to be in series. But between the 4 microfarad and the 1 microfarad, see, there are 2 junctions. So I know that this part is a parallel circuit. There are two branches in that parallel circuit. The 1 microfarad and then the 2 4 microfarads. That's difficult to see. I get it, because partly it's just the way I've drawn it. That I have these 2 capacitors. They look like they're in parallel, but they're not. They're in series, because there's no junction in between them. And I know that seems like I'm just trying to trick you. I'm not. But I like this, because you're probably not ever going to do capacitor circuits, honestly. Probably never. Right? Maybe some of you will. But it is important for your spatial skills. It helps build good spatial skills. Yeah, Emily?
Okay. It's rocking my brain when it's sideways. So when it's sideways, is it still? So let's take that first branch for example, the 2 and 4.
Mm-hmm.
Is that still parallel?
Yeah, that's in parallel, and I can tell that it's parallel. Let me erase all this again. The 2 and the 4 are in parallel because they're contained on either side by a junction. So there's a junction that is at the beginning and at the end of that branch. And that if I have a junction, then I have a parallel circuit.
So when it's sideways, there's a junction, parallel, no junction.
Don't think sideways, or it doesn't matter like how the capacitor is oriented. All that matters is it doesn't have a junction on either side of it. And if it does have a junction, it's in parallel. Trace the circuit. Try not to freak out when you see a circuit and it looks big and complicated. It's not going to be that big and complicated. It'll be similar to this in difficulty. But just trace through and look for the junctions. That's your key. Look for the junctions. Okay? You want me to work through this one? Yeah? Okay. So, I have magenta. It's like my shoelace. You'll see I have magenta shoelace. Y'all see? The dentist lady said that it was pink. I don't think it's pink. Magenta. Huh? Yesterday I went to the dentist, yeah. No, I have other shoes I wear sometimes. But I wear these a lot. I wear them a lot. My wife says I need a new pair of shoes. She's wrong. So I have my 2 microfarad, and then this 2 and 4 microfarad is 6 microfarads. I'm just finding the equivalent. The 4 and the 4 right here, that's 2 microfarads. And then the 2 and the 1 is 3 microfarads. And then I think that's it. Yep, that takes me back. So now I have 3 capacitors in series. You might think that they're in parallel because look, they look like they're in parallel, but there are no junctions. So these are actually, all 3 of these come one after the other. Everything's in series. 2, 6, and 3, that's 1, right? Isn't that 1 microfarad? I think that's right. 1 over 1 over 2 plus 1 over 6 plus 1 over 3. That's 3, 6. 3 plus 1 plus 2. Yeah, that's 1. So the equivalent of this whole thing is 1 microfarad. 12 volts. That means, remember with capacitors, they in series they have the same charge. So I have 12 microcoulombs. That means I have 12 microcoulombs here, 12 microcoulombs here, and 12 microcoulombs here. Then once I know the charge, I can find the voltage. My voltage is 6 volts, 2 volts, and 4 volts. Just to double check that, I can say, well, this capacitor is half this capacitor, so it must have twice the voltage, which it does. And this capacitor is a third this capacitor, so it should have 3 times the voltage, which it does. Okay? So, and then 6, 2, and 4, those all add up to equal to 12. Those are good little internal checks that we can do. And then I can write those voltages over here. Oh, I changed color. So I have 6 volts. This is going to be 2 volts here and 2 volts here. And then I have 4 volts here. And then 2 volts across each of these. Why 2 volts and not 4 volts? Because I have identical capacitors. And capacitors in series split voltages. Capacitors in parallel share voltages, but in series they split them. And since they're identical capacitors, then they split it evenly. And that's it. So if I want to know the voltage, or the equivalent capacitance here is 12 microcoulombs. The voltage on C2, which one is that? That's that 4 microfarad. Yeah, that's this capacitor. It's 2 volts. And then the energy stored on C4 is 1/2 CV squared. And C4 is 2 microfarad capacitors. This one right here. So it's 2 microfarad, 1/2, 2 microfarad, 2 volts squared. That's 4 joules. Or it's actually 4 microjoules. Okay? Gosh, I don't know if there are any energy questions. I don't remember those. Because I wrote the test last week, so it's been a while. Okay? Other particular questions you don't have that you want to work on? Multi-loop circuits, other combination circuits, particular multiple choice conceptual questions.
Do you remember studying when the spring potential?
Mm-hmm. Hold on, I'm not ignoring you. Just looking at something. No graphs. No graphs. We did this in class, in lab, but, huh? I understand, but on your exam, no graphs. Okay? But just FYI, so here, I is equal to 1 over R times V, and so the slope of this graph would be represented by 1 over R. Which we have a similar question to that on lab midterm, right? Is that okay?
So the slope is.
The slope is 2. You say 2 is equal to 1 over R, so R is 0.5. Yeah. Okay.
I just didn't know what to say.
Yeah, so you say 2 is 1 over R. And so R is equal to 0.5 ohms. Other particular questions? I can just sort of scroll through. You all good on the multi-loop circuits? Want to do one of those? Okay. They don't have to be hard. If you know how to apply those rules about the resistors and the batteries, let me just recap those. So if I have a resistor and my current is in that direction and I'm traveling in that direction, it's negative IR. If I have a resistor, my current is in that direction, but I'm traveling opposite the current, is plus IR. Okay? If I go with the current, the resistor does sort of what you would expect it to do. It causes a drop in energy. It's negative. If I'm going against the current, it does the opposite of that. And then with the battery, if I'm going in this direction, that's plus V. If I'm going in this direction, that's minus V. Remember, I like to think of the roller coaster, chug, 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 chug. You're gaining energy as you go up that ramp, and then here you're losing energy as you go down the slide. So remembering those rules will really help you on this. You need to know those rules, just like you need to know all the capacitors and resistance rules. You need to know these rules for the voltages. How are the voltages? Are they positive or negative? Here, to find the currents, the first step is to pick the directions for the currents. I won't give you those directions. Just choose them randomly. Don't give them any thought. Just choose them. Doesn't matter what you choose. And then figure out which loops should you do. And notice here I have no resistor in this part of the circuit. So I'm going to include this every chance I get. That means I'll do the bottom loop and I'll do the big loop. That way the equations are just easier to solve because I only have one unknown, and that unknown will not include I3. So let's pick a starting point right here. We'll go in this direction. That's going to be 4 minus 2I1 plus 2 is equal to 0. Notice that I3 didn't come in there anywhere. A lot of students will try to add in the I3 somehow. Not in there. You're not going to see it. Be careful that you get your signs right and that you get the right current. So current I1 starts here and goes all the way to here. So anything in that part will have I1. So make sure you get that. And then for the bottom loop, let's start right here and go in that direction. That would be plus 6I2 plus 8 plus 2 is equal to 0. Now I can solve both of these. That's I1 equals plus 3 amps. And then this gives me I2 equals negative 10 divided by 6, negative 5/3 amps. I keep those signs until I'm ready to record them. But I want to get I3 as well. I just pick a junction. My incoming currents include I1 and I3 equal to the outgoing current, which is I2. I just looked at these three arrows. Some are going in, some are going out. And then I have some of these. 3 plus I3 equals negative 5/3. Notice I kept the negative sign on that current. And then I3 is equal to negative 5/3 minus 3, which is 9/3. That's minus 14/3 amps. So now I'm ready to record them. I have I1 as 3 amps. I chose I1 to the left, and that's correct. I2 is 5/3 amps. I chose I2 to the right, but that was incorrect. And then I3 is 14/3. I chose I3 to the left, but that was incorrect because it came out negative. The plus 3, is that not right? No, that's right. So the I1 right here, I did 4 plus 2 is 6. I subtracted 6 from both sides, so I get negative 2I1 equals negative 6, and then I divided both sides by negative 2. Sorry, I skipped about 2 steps there. Okay?
Did you figure out the directions?
I didn't. I just, oh, for here you mean, when I did left, left, right?
Yeah.
I had chosen I1 to the left, and because this came out positive, that means I chose correctly. I chose I2 to the right, but it came out negative, so I chose it incorrectly. So I just take the opposite of what I chose because it's negative.
So you flipped your traveling direction?
No, I flipped the current direction. The direction for the current that
How do you decide how to travel?
I don't. It doesn't matter what direction you travel, just as long as you're consistent. Okay? Doesn't matter the current direction, doesn't matter the traveling direction. Just what you choose anyway, just that you apply it consistently.
How did you know to do I-1, I-2 first, and then find out the after?
Good question. So, the reason I did I-1 and I-2 first is because I make this problem easier by not having a resistor in this bottom loop. Because if I had a resistor here, this equation would have some I3 term in it. Because there's no resistor here, when I do this loop, what was this? The big loop? I have 4 minus 2I1. If I had a resistor here, say a 2 ohm resistor here, I would have a plus 2I3. But I didn't put the resistor there for that reason, just to make the algebra easier. And so I do I1 first and I2 first because it's easier to do it. The equations are just easier to solve.
So you did I-1 first, could I have done I-3 first?
No, you can't do I3 first. In fact, you can't even solve for I3 without knowing I1 and I2. Because there's no loop rule that I can write that will have I3 in it. There's no loop equation that I can write. Because there are no resistors, there's no loop rule. I can't do the bottom loop, can't do the big loop. The top loop doesn't have I3 in it either. And the reason I don't write the top loop, by the way, is because when I write that equation, it has I6, I2, and 2I1. Those are both terms in that top loop. So I have an equation with 2 unknowns, and that just becomes difficult to solve. It's not impossible, because you come up with 3 equations or 3 unknowns, and that's solvable, and you've done that before, I know, but it just takes a long time, so I don't think they'll do it. Want to say it or recording?
Hey,
All right?
I just realized you said 415 and not 450, didn't you?
Yeah, somebody else thought I said 450.
That's why I'm so late.
I'm sorry.
It's fine.
You should catch the recording at the beginning of the first 20 minutes or so. All right? Does that answer your question? Yeah. All right.
So, like, just to be sure, whenever you got that negative 5/3 amps, you knew that your current direction was wrong compared to your travel direction, and so you flipped its current direction?
Travel direction doesn't matter. When I'm trying to find the current direction, traveling direction is just the direction that I'm using to go through the circuit to write the loop rule.
So you just really just only changed
The current direction. That's all that matters to me at the end. I don't even think that I asked for the direction, honestly. No, I didn't ask the direction. I'm sorry, that's just an oversight. But if you write the direction, I'll like you more. Okay. I have the exam right here on my telephone. Can y'all see it? You'll beat me up and steal my phone. All right. What? Okay. Other particular questions that you want to look at? Let's look at some of the. Jane, you have a question?
The 2023 number 10 is just found in the concept.
Okay, yeah, that's what I want to look at some of the conceptual questions. 2023 number 10. That's this one, right? Okay, so yeah, there's definitely one like this. So I always like to write the equation that describes this. R is rho L over A. And then I'm making the diameter and the length different. So the length is 4 times the original size. Be careful, okay? Because sometimes I say the area is bigger, and sometimes I say the diameter is bigger. So I say here the diameter is 4 times bigger, and I know some of you are probably going to put a 4 there, but is that going to be right? No, I have to put a 16 here, because area is pi r squared. So area is proportional to the diameter squared. Or you could say that it's pi d over 2 squared. But regardless, it's the area. If I quadruple the area, I'm 16 timing. Excuse me, if I quadruple the diameter, I have 16 times the original area. So 4 over 16 is 1 over 4. So just that, you need to be very careful that you're looking for this word. Is it diameter or does it say area? Because there might be two steps that you have to take. If I say area, then it's just 4 over 4. But if I say diameter or radius, then you have to square that radius, that change in radius or diameter. Okay? You know, be careful with that. Jane, be careful with that. Okay, I'm pretty sure that question's on there. Okay, let's look at some other conceptual questions. Like I told you in class, there are some ranking questions. I'm pretty sure there's some like 12, Mia.
Could you give them the
Yeah. Where it asks you if you get rid of a resistor or if you add in a resistor, what happens to the voltage? So here, if I replaced R3 with a wire, what happens to the voltage in R1? Well, you can think about this in a number of ways. I mean, here I know I have 2 and 2 in series with one another. Right, the equivalent of this is 2 and 2, 2 ohms and 2 ohms. That means I have 6 volts and 6 volts. But if I get rid of one of these, if this one just goes away, then that means that the new voltage across this resistor is going to be 12 volts. So if I replace it, or if I get rid of this resistor, the voltage across this is now going to be 12 volts. This one's going to be 12 volts too. So V1 will increase. There are variations on that question in the concept test, which is on Canvas, and then also in the past exams. We'll scroll through and look for some others. Sagan?
Have you gone over number 12 of 2016 yet?
No, we haven't gone that far back. Let's go with it.
It's just which of the resistors has the smallest current.
16? I don't know.
Oh, you mean the year?
Yeah.
Yeah, 16.
I don't remember what happened in 2016. Number 12? This one? Oh yeah, these are fun. So which one has the smallest current? I know that it's not R1, right? Because R1 actually has the biggest current. All the current that comes through this circuit goes through R1. So R1 has the biggest current of all these resistors. And then after it goes through R1, it comes to this junction, and it splits into 3 different parts. And I want to know which of those is the smallest part. Well, look at our resistances at 4, 6 ohms on this one, 2 plus 4, and 1. So the one with the smallest current will be the one with the biggest resistance, because it resists the flow of electricity the most. So which one is that? Of R1, 2, 3, or 5? The one with the smallest current? Let me repeat what I just said. Splits into 3 parts here. One goes to a 4 ohm, one goes to a 6 ohm resistor. This is a 6 ohm, and one goes to a 1 ohm resistor. Which of these is the hardest path? Right, the 6 ohm. That means that these 2 resistors will have the smallest current, which is C, R3. You have to be careful though, because like if you look at if you say which one is the biggest resistance, you might say R2 or R4, but that's not really what I'm asking. I'm asking which of these paths has the biggest resistance, and it's this path right here, the middle branch, that has the biggest resistance, so it'll have the smallest current.
So why is it not the very first one?
All of the current comes off this battery, goes through that resistor. It doesn't split up at all, but when it comes here, it splits into 3 parts. Okay?
If there was an answer choice for R4, would it be?
Yeah, R3 or R4
I can see like both of them.
would be correct. Yeah, R3 and R4 have the same current because resistors in series have the same current. Okay?
So because it has more resistance and less.
Yes. Because it has more resistance, it has less current. because R is big, I is small. They're inversely related to one another. Okay? Yes. Uh-huh. I don't know where they are, but I have an example I'll show you. I'll just make up one. Imagine I have, I don't know, a 10-volt battery, and I connect it to, I don't know, a 4 ohm resistor, like that. And I tell you that the current through this 4 ohm resistor is 2 amps. Is that right? No, because there's another resistor that's hiding inside of this battery. There's another resistor right there. And so what is the resistance of that resistor? Do y'all know what the resistance is of that resistor? What resistor right here, when combined with the 4 ohm resistor, would give me a current of 2 amps? Hmm? Why 1? Somebody said 1. Right, because a 10-volt battery with a 5 ohm resistor would give me 2 amps. Right? 10 divided by 5 is 2. So I'm missing a 1 ohm resistor somewhere. I have then a 1 ohm resistor, and that 1 ohm resistor, that is my internal resistance of the battery. That I'm getting a current out that is less than what I think it should be. Actually, no, that's more than what I think. No, that's less. I'm sorry, that's less. I'm getting a current that's less than what I think it should be because there's a resistor that I'm not seeing in the circuit. So you'll have a question similar to that. It's not phrased in the same way that I don't remember who asked that. Helen, I think you did. Not phrased in the same way that I've asked that question in the past, but it's still the same question. So I'll tell you, you have a 10-volt battery with a 4 ohm resistor, and there's a current of 2 amps. Not those numbers, obviously. And then I'll ask you, what is the internal resistance of that battery? Is there a formula? Yeah, I mean, I don't know. What is it, like delta V equals E minus I R? I mean, the way you would apply that here is you would say delta V across this resistor, which is 8 volts, is equal to 10 minus 2 times R. Yeah, that's how you would apply that equation. But don't think of it in terms of what are the numbers to plug into that equation. Like, I think you're probably going to make a mistake if you do that. Instead, think, hey, I've got this circuit with a current that doesn't seem right to me. That current is not right. A 10-volt battery and a 4 ohm resistor. So what is the resistor that I need to make that current right? And then that's the resistance that is the internal resistance of the battery. The answer would be 1 ohm, right? Good question. And there is, I think there's at least one buried somewhere years ago that's similar to that. But it's the same question, it's just phrased in a different way. That's what I'm telling you about it now. Okay? Other questions? Yeah? No, we're going to do that next time. What you probably do on a JFC, I guess. The little outlet with the buttons on it, that's reset buttons. I got a hairdryer. That's a GFC. Okay. Other questions? You don't know what that is? You've seen that before. All right.
I don't pay attention to outlets and stuff.
Could you, number 5 and 23?
Number 5 and 23? Okay. Okay, yeah, so here It's how much charge. First, you say V equals IR. I is equal to 6 divided by 3. So I is 6 over 3. That's 2 amps. And then I know that charge is equal to I times time. That's based on the definition of current, Q over T. I think I use a capital Q. We use them interchangeably. And so the current is 2. The time is 5 seconds. So it's 10 coulombs. Alrighty. I'll always stop there. If y'all have more questions, I'll hang around. You can ask, but seems like y'all ready to head out.